Hi guys, today we're going to talk about behavior trees and explainable AI and why naming subtrees is often a good idea. And my name is Petter Agrian. So what's the deal with explainable AI, or XAI, that it's sometimes abbreviated to? Well, it turns out that trust in AI can either be too high or too low, and both are kind of bad. If trust is too high, you can end up with situations like, this is odd, this is an odd decision, but I'm sure there's a good reason, so let's go with it. It's a sign of disaster. Or on the other hand, this system sucks, just ignore it. That's what I usually do. It's not a good sign either, right? So if decisions of the AI can be explained, the users can agree when decisions make sense, and they can also notice when decision does not make sense, either because the assumptions are not valid, like, yes, it's Thursday today, but it also happens to be Thanksgiving, so everyone will be home and you don't have to do what you normally do on Thursdays. Catching corner cases like this is often fairly easy for a human, but difficult for an autonomous system. And by giving explanation, the human can also build a proper trust in the AI, kind of get a feeling for when it's going to work, when the suggested decision is reasonable, and when it's not. And furthermore, by understanding what the AI is doing, given the explanation, the human can be better at predicting what the AI will do, and therefore collaborate more efficiently in situations like traffic environments, factory environments, collaborative assembly, and so on. In almost all cases, collaboration requires you to kind of predict what the person you're collaborating with or the system you're collaborating with is going to do, so you can adapt and move forward. There's also two types of explanations. The proactive, where you can say that I'm doing X because I want Y to be true. I want to achieve something. And the more reactive explanation, I'm doing X because Z is true. So either a proactive example would be, I'm going home because I need to eat, whereas a reactive explanation would be, I'm going home because it's 6 p.m. So there are some human autonomy teaming guidelines in this excellent report by Mika Ensley, published by the United States Air Force, called Human Autonomy Teaming. So the suggestions or guidelines are that the AI should be congruent with how humans parse problems and form solutions. Avoid anthropomorphisms, such as having a human face and a natural sounding voice, giving the sense of the AI having all the capabilities that a human usually have. It should be transparent and traceable in the sense of the system must be able to explicitly explain its reasoning in a concise and usable format. It should also support robust visualizations so you can see what's going on at different levels of resolution and abstraction. If you want the details, you should be able to get the details of the explanation. But if you want a high-level explanation, that should be possible too. It should also enable self-health assessments, kind of understanding when its information is not updated and so on, and support joint training. This is more specific to the Air Force needs, but basically in a factory you're using the system, so there's no significant difference between training and doing what you're supposed to do in most circumstances. So we're going to see that backward chain behavior trees and also decision tree type of behavior trees can achieve this kind of transparent and traceable explanations. And in fact, all BTs have different levels of resolution and abstraction in terms of the subtrees, where you can expand and collapse subtrees and see what's going on inside modules in details, or just see on the higher level what modules are active or what subtrees are active. And as we hinted in the title, this is going to be connected to given names to all subtrees. That makes sense and can support explainable AI. We're going to see more about that shortly. So can a behavior tree provide explanations regarding what's going on? If we just look at the behavior tree, this is supposed to be a generic behavior tree, say this node is executing, then if you know how behavior trees works, and obviously you would know that this guy would probably have returned success for this guy to be ticked, this guy would have returned failure, and there should be a success from somewhere here, and so on. So we can see what conditions returns true and false, and therefore kind of understand what's going on. But that kind of holds for all the computer stuff, right? You can, since a computer executes in a predictable way, you can always kind of explain what it does by looking at this software. But we want something more explicit and more readable to a non-expert than that. We can also see what operating region the behavior tree is in. So you might remember operating regions from another video where we looked at how you can see a behavior tree as a discontinuous dynamical systems. We looked at operating regions. So it basically meant that whenever you're inside this is a state space, so whenever you're inside this omega-1 region, some subtree, the subtree 1, whatever subtree that is going to execute. And when you enter the omega-2 region, another subtree is going to execute, and so on. So then you can explain, what is it doing now? Well, it's doing this because it's in the omega-2 region, but it's also a bit technical. What about hierarchies and modularity? We're going to see that we can get some answers from these areas. So we know in behavior trees there are few dependencies between subtrees in modules. So what's happening down here should be connected to the closest subtree and the next closest subtree, and it should be less connected to what's going on over here. So there should be some kind of local explanations inside the subtrees. Explanation should be found in the current subtree. And there's also a natural hierarchical order of actions in a BT, as well as in most actions we do in the real world. So imagine you're preparing food, then maybe you want to get milk as part of your food, and in order to get milk you might want to open the fridge, and in order to open the fridge you might want to grasp the handle. So reversing this, you get some kind of explanation, right? So I'm grasping the handle in order to open the fridge, in order to get milk, in order to prepare food. That kind of makes sense to most humans, I'd say. So how do we use these ideas? We want to look at subtrees, we want to use modularity, we want to use the hierarchical orders of behavior trees in a nice way. And a related question that you might ask is, does the behavior tree design principle matter? We've seen that we can do decision tree designs, we can do backchain designs, we can use genetic algorithms to design our tree for us, and so on. And it turns out that the design principle is going to matter. In some cases, it's much easier to kind of find an explanation for what's going on in the tree than in others. So let's start by looking at one design principle, the decision tree design. And this example is also from another video on using the decision tree design principle. So this warrior here, lovely guy with a spear, basically first checks if there's an enemy nearby. If so, we check if the enemy is very close. If so, we attack. If not, we check if the health is low. If so, we hide. If not, we approach. If there's no enemy nearby, We check if we're hungry or tired. We might be eating or sleeping or wandering, and so on. So just looking at this BT, now we're going to use this idea of naming subtrees to make this more clear what's going on. So this is one way of naming the subtrees. So as you can see here, most of the nodes, the fallback and the sequences now have a label to them that basically just provides information. It does not change the execution of the tree in any way. So for instance, we've named checking if enemy nearby here, then we're executing this subtree. So basically we put that label on this sequence node here, because whenever we're in this subtree, that means the enemy is nearby. Otherwise we'll get a failure here and we're going to execute the other subtree. And here we put the label, the reverse label, enemy is not nearby. Similarly here, enemy very close, then we do this. So when the enemy is very close, we're going to execute this subtree. Otherwise we're going to go over here, and here we wrote enemy is not very close. So adding these labels, if we have a decision tree, behavior tree design, we can get explanations as following. So if we're hiding, for instance, we can just read the labels of the subtrees. So I'm hiding because there's an enemy nearby, but the enemy is not very close, but my health is low. Therefore I'm hiding. And this would make sense to most humans, I'd say. However, we should note that this is kind of a reactive explanation, not a proactive. The objective, well, it's clear to most humans that we're hiding. Hiding makes sense if the health is low, if we're a warrior kind of guy, because we know that fighting with low health is probably a bad idea, because then you might die and not perform so well. But it's not clear, it's not explicitly clear that hiding is going to kind of solve the problem we're in. We just know that it makes sense given our knowledge of warriors with spears. So another example. So the agent is sleeping. Why is it sleeping? Well, there's no enemy nearby, we're not hungry, and we're tired. Therefore we sleep, which kind of makes sense. But it's still implicit, because we know that sleeping is going to make this tired thing go away and enable us to do something else. But it's not clear from just the labels here what we're trying to achieve by sleeping. We're sleeping because we're tired. And another thing to note here is that if you actually want all the labels, here we had enemy nearby and enemy not nearby. If you want all the labels, you need to add extra labels on the bottom line here, because here we have health low, but there is actually no kind of node here where you can add the label health not low. So if you really want the kind of the positive and the inverse on all the subtrees, you need to add this label either to this action or to a decorator that you add in here. But the idea is the same. So now we're moving on from the decision tree kind of designs, which are a fairly narrow class, to other designs. So this is a mobile manipulator example that we looked at in the video on operating regions and seeing behavior trees as discontinuous dynamical systems. So we have a mobile manipulator. What it's supposed to do is go to an object, grasp the object, and drop the object at goal. Then the object is at goal and it's happy. So let's call the whole tree for as behavior tree 0. So then the success region of tree 0 is the object at goal. When the object is at goal, this guy is going to return success, and the whole tree returns success. So the subtree 1 over here basically does not have an operating region, because this is just a condition saying true false. So let's look at subtree 2 here, object in hand, drop object at goal. The operating region of this guy is, first, this guy needs to fail for this guy to be ticked. And then if this guy is true, then this guy is going to execute. So the operating region is when the object is not at goal, but in the hand, then this guy is going to execute. Let's look at the next subtree, grasp object. For that to execute, this guy needs to return failure, this guy needs to return failure, and this guy needs to return success. So not at goal, not in hand, and near agent. Then this guy executes. And looking at the last subtree, go to object here, that only executes when all these return failure. So not at goal, not in hand, and not near agent. So then you can say, okay, so why are we executing go to object? Well, one explanation is the object is not at the goal, it's not in the hand, and it's not near the agent. But the kind of a more human explanation would be this. I'm going to the object in order to get near the object, in order to grasp the object and put it at the goal. But that's not clear from the the operating regions. And as we've seen here, the operating regions are designed so that executing drop object at goal will result in the object being at goal, and similarly grasp object is designed to get the object in hand, and go to object is designed to be near the object. So we have this kind of transitions, and this is a well-designed behavior tree. It's going to reach the object if every low-level action does what it's supposed to. But we're getting reactive explanations. Why are you doing this? Well, because the object is not at goal and not in the hand and not near the agent. We want these proactive explanations as well. Before we look at an example where we can actually get proactive explanations, we just briefly review genetic algorithms that were also discussed in another video. So remember, we had a bunch of behavior trees, we select the best, we do some crossover between them to get new individuals, we do some mutations to get even more new individuals, we evaluate them, we select the best, and then we iterate this loop, and then we get better and better designs. So this is an example that was done for the Mario AI game. And as you can see, it's fairly structured, and a lot of this structure comes from the anti-bloating by collecting conditions that we discussed in that video. So using genetic algorithms, you can get results that look much worse than this. But still, okay, so why are we shooting? Because there's an enemy in cell 14. Why are we jumping? Well, because there's an obstacle in cell 12. That kind of makes sense. But it's, again, implicit that it makes sense to jump when there's an obstacle here, just because we want to get over the obstacle. It makes sense to shoot when there's an enemy here, just because if we do that, the enemy is going to die. And that's not clear from this design. We need to have all our kind of human knowledge of the Mario world to understand that it makes sense. So we want this proactive explanation that why are we doing stuff? And it turns out we can get those from backchained BTs. So this is an example of a forklift. So just to let you know what the scenario here is, we have the forklift, the autonomous forklift over here, that wants to move this object to the goal over here, and then go back to the charger. And all the while it's kind of disturbed by this humanly operated forklift that moves around. It has an unsafe area that we need to stay out of. So that's the example we're going to look at. So this is a behavior tree for executing these actions. It's fairly big and it has a lot of text in it, but we will see that we can actually get explainable actions from this tree in a fairly transparent way. So just reminding us briefly how backchaining, there's two other videos on backchaining. So basically you have a bunch of subtrees of this structure where we want to make sure something is the case. First we check it, And if that's not, if it is the case, then we're happy, returning success. If not, we try to fix it by doing different things. So this is an example of this structure. We want to make sure in the safe area. First, we check if we're in the safe area. If so, we're happy. If not, we move to the safe area, but we can only do that if there's a free path. And then the whole design starts with a bunch of top-level goals up here. Make sure in safe area, make sure in range of charger, make sure object at goal, and make sure robot at charger. So a bunch of top-level goals, A, B, C, and so on. And then the whole backchaining is that we replace a top-level goal with a subtree that achieves it. So make sure X here, we replace this by the make sure X subtree. And then we have maybe a precondition Z1 here, and then we have a subtree for achieving Z1, and then we replace this guy, and then we get something that looks like this. But note here that this is slightly different from earlier videos on backchaining, where we just had fallbacks and sequences. Here we added labels to those nodes, and therefore labels to the whole subtree, just as in the decision tree design example. So just to make this clear, what the difference is here with this kind of make sure thingy. So imagine we're talking about ice cream, which is nice. So there's a difference between make sure we have ice cream, check if we have ice cream, and buy ice cream. So if I ask you to buy ice cream, you would probably buy it, no matter if we have it or not. If I ask you to check if we have ice cream, you're going to check in the fridge and say, yes, we have ice cream, or no, we don't have ice cream. But if I ask you to make sure we have ice cream, I want you to kind of first check, and if we have, everything is dandy, you're done. If you find out that we don't have ice cream, I want you to do something about it, either buy ice cream, or I don't know, make ice cream, or steal ice cream, or whatever ways you have of making sure we have ice cream. So that's why naming these small subtrees that first check something and then try to fix it, I think naming them make sure X, make sure we have ice cream, makes sense, because it kind of encapsulates the fact that I want you to check, and if we're already done, we're happy. But if it's not so, if we don't have ice cream, I want you to do something about it if you can. So that's why all the subtrees here with a fallback at the root. So this guy and this guy and this guy are labeled make sure, yada yada. Yeah. So, and here with this make sure thing, all of a sudden we have access to why we're doing something. Now we're buying ice cream in order to make sure we have ice cream. Now we're grasping an object in order to make sure the object is in the gripper. So can we get explanations here? Well, I just hinted at the answer. So let's pick an action, move to object down here. Then we trace the path to the root from move to object. And now if we read the labels here, we get a fairly explicit explanation for why we're moving to the object. So it actually makes sense to read this bottom up here. This is just listing this, but we're moving to the object in order to move to the object, in order to make sure the robot is near the object, and we want to be near it to grasp it if possible. We want to grasp it in order to have it in the gripper. We want to have it in the gripper in order to place it at the goal, and we want to place it at the goal in order to make sure it is at the goal. That's one way of getting it to the goal, by placing it there ourselves. So this makes a lot of sense, I'd say. It's transparent, but there's also a lot of text here. You might say, oh, this, I can't handle all these details. It's just too much. I'm overwhelmed. I want less details here. So you can also just read the fallbacks, just read the make sure if you want to. So I'm moving to the object, so we're skipping the sequence here to make sure the robot is near the object, to make sure the object is in the gripper, to make sure the object is at goal. if you want less details. And this works at any level of abstraction. If you imagine you collapse a subtree here, you can just read the make sure things, and then you obviously you get less details, but it still makes sense in a proactive way. So if you just cut here and you're doing something, instead of saying I'm moving to the object, you can just say, what is the robot doing right now? Well, it's making sure the object in the gripper in order to make sure the object is at goal. So another example, we looked at move to object here. Let's look at move to goal here. Why are we moving to the goal? Well, to make sure we're close to the goal, to make sure the object is at the goal. But we can actually provide more detailed explanations by also saying what important sub-goals we have achieved and what important sub-goals we have not started to look at. So for instance, we ask the robot, what are you doing? I'm moving to the goal, but it can actually start by saying, achieved important sub-goals, I'm in the safe area, the battery level is at the proper level, I already have the object in my gripper, and given this situation, I'm moving to the goal to make sure I'm close to the goal, to put the object at the goal, since I already have it in the gripper. And I haven't started to worry about being at the charger yet. So we move to the goal. Why? Well, the important sub-goals, and if you check the video on why backchaining of 4 common bugs in backchain designs, you know that these are called the ACC, the active constraint conditions. We're in the safe area, we have a proper battery level, and we have the object in the gripper. So actually, by executing move to goal, we don't want to violate them. We don't want to move into the unsafe area, because then we're going to switch back here. But that's another story. So these are the important sub-goals, the current action, and then we just read it from bottom to top. I'm moving to the goal to make sure I'm close to the goal, to make sure the object is at the goal. And then the sub-goals not addressed yet. Sub-goals to be addressed is robot at charger. So when we actually execute this, so this is an example from the Unity environment where there's something called Panda behavior trees that looks like this. I think they're fairly neat and easy to use, and they're free as well. And there's a free version and a non-free version, but I'm happy with the free version. So basically just seeing what we just saw, how that looks executing it. So the achieved sub-goals, they're basically the things returning success here, and therefore green in safe area, object in gripper. So here we actually don't, in this example, we didn't check the battery level during execution. We just went back to the charger. So this is not on the right here. But those are the sub-goals achieved, and then the current action is move to goal. So we start here, and the blue stuff is the stuff being executed, returning running right now. So we just move to goal, and then we read the fallback. This is a sequence, so we're going to jump over it. We're moving to goal in order to make sure we're close to the goal. We're skipping a sequence in order to make sure the object is at the goal. I mean, you can read that if you want to, but if it's too much details, you just go for the fallbacks. So this is what we just saw on the other slide, but actually executing. And it's even easier to find it when it's executing, because then you can check the sub-goals or the guys returning success, and the trace to the root are returning running here, and therefore blue. And obviously the top stuff here is make sure all the sub-goals are achieved. The report from the US Air Force said that being able to get explanations on different levels of abstraction was important. And we kind of hinted at we can use the level of abstractions inherent in behavior trees, that is the subtrees, to actually get explanations at different level of abstractions. So let's see an example of that as well. So now we're moving to the goal here to get the object in there. So we can see that the important sub-goals are, we're in the safe area, we have the object in gripper, Yeah, we actually have animations here. And right now we're moving to the goal, and in order to make sure we're close to the goal, and in order to put the object at the goal. So let's see if we want this on a less detailed level, on a higher level of abstraction. So in this Panda BT, and I think in many other tools, you can kind of collapse subtrees by just clicking this arrow here. So doing that, it's going to look like this. So now we've collapsed line 4, line 9, and 35. So 4, basically, this make sure safe subtree is collapsed. And line 9, this whole subtree is collapsed to make sure object at goal. So then the exact same situation, then you can get the explanation. Important subgoals achieved. I'm in the safe area. This is the unsafe area. And what are you doing right now? I'm making sure the object is at the goal. No more detail than that. All right. So let's see how this looks when we actually run the examples and the colors are changing here and the stuff is moving. So we have the behavior tree on the right and everything starts moving, and now we pause the execution to check what's going on. Right now we're doing tasks to earn money, to make sure the robot has money to pay another agent, because we can't really access the object right now. Now the human forklift is going to move so we can access the object. We're pausing again, and now we're moving to the object in order to get to the object, make sure we're near the object, to grasp it, to have it in the gripper, to put it at the goal. Moving again, so now we have the object. Well, now we're grasping the object in order to make sure it's in the gripper, to put it at the goal. So now we're moving towards the goal, move to goal, to make sure we're close to the goal, to put the object at the goal, and so on. We're running the system again. And now we actually moved it to the goal, and we can see that the object is at goal. We're moving to the charger. We're going to move it out again. So now we need to go back and grasp it, putting it at the goal again. Place object at goal, and so on. And now we're finally allowed to put it there. We're going back. And now everything is dandy. The whole tree returns success and all the sub-goals are achieved. So, looking back at the human autonomy teaming guidelines from the US Air Force report, which is, by the way, available for free. If you want to read it, it's well written and interesting, I'd say. So we wanted the AI to be able to be congruent with how humans parse problems and form solutions. And I'd say the whole backchain behavior tree design is fairly reasonable to humans. So I'd say I put a tick mark there. The system must be able to explicitly explain its reasoning in a concise and usable format. And I would say that this proactive explanation of I'm doing this because I want to achieve that, because I want to do this and achieve that, is concise and usable. We have visualization as usual in all behavior trees, and we also have the explanation as different levels of resolution, because you can collapse subtrees, avoiding seeing the details. Just reading the subtrees that are not collapsed so far will give you a high-level explanation of what's going on. So thank you for watching. If you want to learn more about behavior trees, we have this book that's available for free on archive and not for free on online bookshops. And I'll see you around.